All right, here's sort of the bonus material beyond just the basics for the proof of the law of cosines and why sometimes the law of sines won't work. Okay, so this is in your book. This is just proof of why the law of cosines works. So this is your generic triangle ABC, and they picked it so that angle A was an obtuse angle, and that's fine. If it didn't work out this way, you could spin it so that it did. Actually, big angle A doesn't have to be obtuse even for this to work, but this will work kind of in any order. And notice they are going to prove it for the way I keep citing it, where we're talking about c squared and angle C being this last thing here. So they drop altitude h here, so we have plenty of right triangles, or two right triangles anyway, and we're going to base a lot of this on Pythagorean theorem. They define this side to be x, and then of course this side would be a minus x if this whole thing is a because it's opposite to a. So the original a, b, and c are labeled as the original law of cosines theorem as you're used to seeing. So this is just Pythagorean theorem here, that c squared being this thing over here, in this direct triangle on this side, we have a minus x is one side, h is another side, and c is the hypotenuse. So that's just Pythagorean theorem. I'll write the rules in here. This is Pythagorean theorem. Why is it that this happens? Well, all they did here is they just did some algebra. They just did the binomial expansion of x minus h squared. Then how do we know that x squared plus h squared equals b squared? That's the right triangle over here. So it's another version of the Pythagorean theorem. Then how come c squared equals a squared minus 2ax plus b squared? Because they just took this x minus h squared business here, and notice they have another version of x squared minus h here. They just substituted this b squared in for that part. So they just did a little substitution like they were solving a system or something. Another expression for h squared minus x squared. I'll call that substitution. That's pretty clever. All right, then they leave that for a while and they say, well, what's the cosine of c? The cosine of c should be x over b because that's just the definition of cosine. Cosine is adjacent over hypotenuse. And in that little triangle where we made a right triangle where c is a right angle, then adjacent over hypotenuse is just x over b. Okay. Then they just multiply both sides by b. That's technically the multiplication property of equality, but I'll just call that algebra because it's pretty simple. And now we have an expression for x. So instead of saying x here, they just substitute this whole thing in for x and put that there. 2a times this thing for x is b cosine c. This is substitution, and now we're almost there. They just rearrange this so that, they just kind of commute this little thing here. It's not even really algebra. That's just commutative property of addition, really. They just move this and reorder it. So there you go. C squared equals a squared plus b squared minus 2ab cosine c. X was integral in that whole thing. Notice there's x all over this thing, but they substitute its way out of it, so they write everything in terms of a and b and c. Pretty cool. Yeah, well, what's this note at the bottom? The area of the triangle. Oh, yeah. The area of a triangle is also half AB sine C. We're not really doing area now. Well, we can talk about that in class. I'm not going to put that in this video. All right, so here's the big thing that, quite honestly, I'm kind of sick of making level 4 questions about this. If you look at my old quizzes and tests and things, you'll find tons of examples of level 4 questions based on this whole thing. Sometimes this is referred to in geometry circles and at math parties and stuff as the ambiguous case. It happens a lot that this is talked about because there are lots of things later in geometry that get kind of equivalent to this. Anyway, this actually came up already this year. This came up when we were talking about side-side angle and why side-side angle doesn't work. If you just look at what's kind of given here, we're given here that this angle is 24 whatever degrees, and we're given that this side is 12.73, and we're given that there's some other side that's 5.81, and that 5.81, it turns out you could lay that side of 5.81 here down from B to the other part of this angle here that's kind of fixed, or you could lay it down this way in such a way that this could kind of flop either way, and what makes what looks like here is an isosceles triangle. So we could have side-side angle make two triangles. So notice triangle ADB and triangle CDB. Both have side, like this side, and the angle. This side, and the angle. are all in agreement, but the two triangles are different. So that was a problem with SSA, and that leads to the exact same kind of problem, the same ambiguity we're talking about when we deal with law of sines, if this is the kind of thing we're handed. So notice what we're trying to apply law of sines here to when we have two sides in one angle, and I said in the last video that that's kind of a problem. You shouldn't really be doing that. You should only be using law of sines when you have two angles, at least. So yeah, and notice if you had these two different triangles that are possible with these measurements, all the other angles are in question. Like this angle at B in the triangle ADB versus CDB, the angle at B could be two different things, and the angle, the third angle, this obtuse version or this acute version could be two different things. All right, so let's see what happens if what are the implications here for trying the law of sines? So we know this side opposite, whether it's this way or this way, this side opposite angle D is 5.81. So you'd think you're doing pretty good if you say sine 24.28 over 5.1 equals something else, like sine C over 12.73, or sine A over 12.73, or even sine B over whatever this side length down here is supposed to be. Anyway, let's just talk about C right now. If you're trying to do this with C, you'd get that the sine of C, because we have three other things in this proportion all done. If you did that, you'd solve for sine C, and you get this. Well, notice that's if we're doing like the big triangle DBC. If we're trying to do triangle DAB, we do the same thing. This is still the 5.81. We do the same whole thing, sine 24.28 over this 5.81 equals sine of this angle at A here over 12.73, and we get the same exact value for sine. Notice this proportion is entirely the same as this proportion here. The only thing that's different is I have these different angle labels. These angles are totally different angles, but they turn out, because of the proportion, they'll turn out to have the same value in the proportion. So they both turn out to have the same, it looks like sine C equals the same thing as the sine of angle DAB. Well, it actually turns out that sine of C and sine of angle DAB, remember we talked about how one of these is acute and one of these turns out to be obtuse? And we never really talked about obtuse angles in sine and cosine. But it does turn out that there is for every acute angle, there's an obtuse angle that has the same sign. And this is one of those times. So these two angles, this angle here at C and this angle kind of on this side of A, actually both, like this is all true, but they both have the same sign. Well, this is a problem if you know the sign first and you're trying to find the angle. It's like, well, if I take the inverse sine of this, how do I know which one it's supposed to be? So this is a problem. I got two angles that have the same sign. I try to do inverse sine, and I'm only going to get one value, so that's not cool. Also realize that the two angles that we're talking about, this angle here that we would be getting at C, that was a really bad angle, Mark. This angle we would be getting at C, that's equivalent to the angle we would be getting on this side of A, and the other angle, DAB, is this angle here. So these two angles that I was saying kind of miraculously have the same sign. The two angles that have the same sign are supplementary, so it's not like they're completely unrelated, but we kind of have a problem. So if you inverse sine that one, this thing I did on the last page, you get an angle size of 64. Well, guess what? That's the acute one. So this thing is 64 whatever. The supplement to that is 115 point whatever. If you take the sine of that, you get the same thing. So both, and you can try this on your calculator, both of those angles will give you the same sign. So that's the problem. We can kind of use that to our advantage sometimes, and again, that's the thing I'm kind of sick of making level 4 questions about. But just realize, if you try law of sines in a side-side angle situation, and you do inverse sine in your calculator has been told to tell you the acute version no matter what, but just realize there's also an obtuse version that could be in there that has the same sign. So feel free to read this paragraph, but that's essentially what's going on, is that side-side angle is a problem. The sign of every angle is kind of not unique in the terms of if we inverse sine some ratio, we get it, the calculator will always give you an acute value, but there's an obtuse value, which is actually the supplement to that, which will produce the same sign. And again, feel free to play with this in your calculator and see how that looks.